we're going to play a quick game of Would You Rather. Would you rather live in a world where there's one infectious zombie that bites 2 people every single minute? Or would you rather live in a world where there's one zombie and he just bites 1 person every minute, but every single one of those zombies can now create a zombie as the minutes pass by? So welcome to Math Mini Lessons. This is Lesson 101. We're going to talk about writing rules for geometric sequences. And so here is our criteria for success. We're going to find a common ratio, and that means being able to identify a pattern of multiplication between 2 consecutive terms, and substitute the R, that common ratio in the term, for an explicit and a recursive rule. So what did this have to do with zombies? Well, let's take a look. In our first situation, we have a growth pattern that's just adding by 2. So we're starting off with 1 zombie. Let's try and figure out what the first 5 numbers in the sequence would be. He bites 2 people, now there are 3 zombies. He bites 2 more people, there are 5 zombies. He's biting 2 more people, there's 7, and he bites 2 more, there's 5. So in this situation, in world A, this would be the sequence of zombie growth that you would see, where you're just constantly growing by +2. And we just talked about these sequences. But what happens if instead of a growth pattern of +2, you have it multiplying by 2? So let's look at world B. And in world B, you start off with 1 zombie and he bites 1 more person. So now there's 2 zombies. And now they bite, each one of them bites another person. So now there's 4 zombies. And now all 4 of them bite someone. So now there are 8 zombies. And now all 8 of them bite somebody. And now there's 16 zombies. So here are the first 5 in world B, first sequences. And here, instead of adding by 2, we are multiplying by 2. So this is a rapid growth. Rapid growth model. And we talked about this a lot when we talked about exponential models. So thinking about this, which world would you rather live in? One that grows at a constant rate with a constant difference of 2, or a constant ratio of 2. And that distinction does matter, because now that we're talking about multiplying, we're talking about rapid growth or rapid decay. Geometric sequences have a common ratio and not a common difference. This means the ratio is consecutive and constant. You are constantly multiplying by that ratio R. So it's a multiplicative type of sequence. Now, you could be multiplying by a whole number where it's getting bigger, like times 2, a doubling. But even if you were multiplying by a fraction, you would still get, it would still change, but really fast, except you get smaller really fast. So this is drastic. Well, I'm going to call it another word. We're going to call this fast growth. And when I start doing my money lessons, you're going to learn that in cases like this in geometric sequences, time is a superpower, because things grow slow at first and then they go really fast. So let's look at the 2 different types of rules. So we're going to start with the recursive. And with the recursive rule, you're still going to have your previous times your common ratio. So let's say it's the previous number if it's a doubling rule. So if I'm doubling, like we saw in our problem, the times 2, then it would just be the previous, which would be, we know how to write that now, which would be f of n minus 1 times r. And in this case, it would be f of n minus 1 times 2. That would be our recursive rule. And we think recursively. We can look at numbers and see if they're doubling or tripling. You can just see it. The explicit rule would be our first term, our first number, times our ratio to the n minus 1 power. So this is exponential growth. I think I spelled that wrong. Exponential, I did. exponential growth, which is very fast. It is rapid growth or decay. Okay, and why is that happening? That's happening because instead of repeated addition, here we have repeated multiplication. So let's look at this pattern, and again, you can think about it as zombies if you want, but it is a doubling pattern. Here it's just number of folds and layers, so every single time you fold the paper, how many layers do you have? And you'll notice I could think of this as a growth number, so in the beginning it might look like +2, but you're going to notice that it doesn't work after the second term. So if you notice it is growing and it's not arithmetic, it may be a multiplication pattern. And here, the only way I can go from 2 to 4 is to multiply by 2. So times 2, times 2, times 2. So my R is equal to 2. That is my common ratio. Sometimes you're not going to be able to see it, so it sometimes helps to just take the two terms and divide them. So that can help. You can just take the next two numbers, like what if I took 8 and 4? And you can turn that into a ratio, and you can see the common ratio simplified is 2. And I could do that again. Whoops, sorry, 16 over 8 is 2, and the last one, 32 over 16 is 2. So you can see it does have a common ratio between them. Once you have that, to write the recursive rule, remember you're doing the previous times R. So f of n is equal to f of n minus 1 times, in this case, 2. That's all you would write. To write the explicit rule, we're going to find the first times R to the n minus 1. So f of n is equal to our first term, which is 2, times 2 to the n minus 1. So that is what we have for now. Let's use that rule to figure out any of the, well, we have the sequence up here already, but if you wanted to see how to work it out with our forms, we would literally just put in the numbers. So if I wanted f of, let's say I wanted the 10th number, then I would take my first term, f of 1, times r n minus 1, or in this case, it would be 2 times 2 to the 9th power. And for that, we would have to use our calculators to figure it out. So that's the other thing about this. Now that our numbers are getting rapid, we might have to use calculators. So I'm going to go through this one model just to show, instead of having a guided practice, we're going to do the same thing. We have to figure out what the R is and what f of 1 is. F of 1 is easy to see. We can just see it on the chart. It is 2. So let's find what the common ratio is. And so if you're not noticing what it is, you could just do 6 over 2, 18 over 6, 54 over 18, and 162 over 54. So let's set up that calculator. The first two are pretty easy. I can see the common is just 3, but let's just make sure with the other ones. 54 over 18, 3. And 162 over 54, 3. So our common ratio is 3. Super helpful, so we can just write down what our explicit rule would be, which is our previous times R. So in other words, f of n minus 1 times 3. Super easy, not much we can really do with this. No, we cannot distribute the f with the n because we're talking about a function here. But let's go to the recursive one. And here we would have f of n is equal to our first term, f of 1, times r to the n minus 1. So we can simplify that out. F of 1 is equal to 2. So 2 times 3 to the n minus 1. All right, and we may be asking ourselves, why can't we just do what we did last time and simplify this? Like, could we just multiply these parts? So, but remember, we have to use order of operations, and in our order of operations, exponents come before our multiplication. So we cannot simplify this by doing 6n minus 1. Can happen. Also can't happen because these are different bases. Now, what if it was 3 times 3n minus 1? Could that work? Yes. If that was the case, then we could have just combined them and actually gotten 3 times 3 would have been 9n minus 1. So we'll talk more about those a little bit later, but I hope you found this really helpful. Remember, all you're looking for today is that common ratio and then substituting the r for the first term in the rule. That's it for today. I'll see you in the next one. Be well.